Thank you for the warm invitation. It's a pleasure to be here. And okay, let me just get started. So, I will be talking about factors of sparse polynomials. And this is joint work with Vishwas Bhargav, who's my student, and Ilya Volkovich, who is right now in Boston College. So feel free to ask lots of questions and interrupt and slow me down as needed in the talk. So let me set up what I will be talking about. So let me define what is sparsity of a polynomial. So when you're given for any polynomial f, suppose so we're thinking of multivariate polynomials. So think of n to be some growing parameter. So f is a multivariate polynomial and every variable has bounded degree. So suppose d is an upper bound on the degree of any variable in the polynomial. We define the sparsity of f, which I denote by f with these lines around them. The sparsity of f is just the number of non-zero monomials in f. So for instance, here is a polynomial f with sparsity 4 because it has 4 monomials. And in general, when each variable has degree at most d, then the sparsity can be as high as d plus 1 to the power n, because there are n variables and d plus 1 choices of degree for each variable. And in this talk, I will focus on sparse polynomials, think of the number of monomials to be few. So it could in general have exponentially many monomials, but the interesting setting for this work will be when the polynomial has much fewer monomials. And sparsity is again a natural complexity measured and well studied for polynomials. So the big question is, if your input is a sparse polynomial, how do the factors of these polynomials look? Can you say that sparse polynomials have sparse factors? Okay, so let's see some examples to see whether we can even hope for such a thing to be true. So this question was studied by von Zurgathen and Kaltofen in 1985, and one natural example that comes up if you think about it is the following. So suppose f is the polynomial, which is the product of I going from 1 to n of xi to the d minus 1. Then note that xi to the d minus 1 factors as xi minus 1 times 1 plus xi square plus dot dot dot, so on and so forth. So if you look at the polynomial f and then you look at the polynomial g, it's easy to see that g is a factor of f, because term by term, like the summation xi to the power j is a factor of this xi to the d minus 1. So g is a factor of f, and notice that f had 2 to the n monomials and g has d to the n monomials. So though g is a factor of f, g has many more monomials than f has. In fact, g has something like the number of monomials in f raised to the power log d, many monomials. And it was conjectured that maybe this bound is tight, like you can't have a bigger blow up in the number of monomials than this. Such a quasi polynomial blow up is the biggest blow up that can happen. Maybe this always holds for any sparse polynomial. The factor of that sparse polynomial has the number of monomials being at most quasi polynomially larger than the original polynomial. Okay, so this might be a true conjecture, but there are some pathological cases. So let me give you an example of another polynomial. So suppose you're working over your field is fp, where p is prime. Then if you look at the polynomial f, which is summation xi to the power p. So p is the characteristic of the underlying field and p is the exponent of these xi's. Then notice that summation xi to the power p is the same as summation xi and the whole thing to the power p. And so if you look at the polynomial g, which is summation xi to the power d, for any d less than p, g divides f. And here it's easy to see that f had only n monomials, but g has many monomials. It has something like n plus d minus 1 choose d, which is roughly n choose d, which is roughly n to the power d many monomials. So the number of monomials in G wasn't just quasi-polynomially larger than the number of monomials in F. It was in fact f to the power d, not f to the power log d. Okay, so there is a bigger blow up here in this example. So if d is large, so the conclusion is that in general, without imposing other conditions on the underlying field and things like that, if d is large, then the factors of g could indeed have exponentially more monomials in f. This is exponential in d because its number of monomials in g was number of monomials in f raised to the power d. But if the characteristic is 0, maybe the first example was the tight example, and you can't have such a big blow up. So we don't really understand which whether these examples do lead to tight bounds or not. We don't know. But what we're going to do in this work is we'll think of d to be small, bound the individual degree. So when I think of d to be small, I mean, you could think of d to be 5 and still ask the question. You have lots of variables. You have an n-variate polynomial. Each variable has degree at most d, but think of d to be small. And I mean, 5 is a good number to keep in mind. And I said, what is the best bound we can prove in this situation on the factors of sparse polynomials? Okay, so let me tell you what is known in this setting. So for d equal to 1 and d equal to 2, these two cases turn out to be not much simpler, and we know good sparsity bounds. We know that when the individual degree d is 1, which corresponds to multilinear polynomials, and when d is equal to 2, and these are multi-quadratic polynomials, in this case we know that the factors can't be more dense than the underlying polynomial itself. For larger values of d, the best we knew was this work of Oliveira, he showed that if you have a sparse polynomial where each variable has some degree d, which is a constant, then the factors, he wasn't able to show that they are sparse, but he showed that they could be computed by small depth 7 circuits. I won't say more about this right now. And Dewey and Oliveira attempted to understand the sparsity of factors for general polynomials, and they had lots of very nice ideas which inspired what I will be talking about in this talk. So the main theorem that we show is that for any underlying field, if f is a multivariate polynomial which has s monomials and each variable has degree at most d, and again think of d to be any constant, then the sparsity of f, so the sparsity of any factor of f is at most s to the power d square log n. Okay, so when d, you think of d to be small, then the d square term is not so significant, and you have this quasi-polynomial blow up, quasi-polynomial in n blow up. And a priori, it was conceivable that this factors could have sparsity the maximum possible, which is d plus 1 to the power n. Even when d is constant, it could have had exponentially many monomials, a factor, but we show that when d is small, it has only a quasi-polynomial in n blow up in the number of monomials. So for any d larger than 2, this is the first non-trivial bound. And in I'm saying the bound is the field of oblivious, and that's somewhat tight. Let me tell you what I mean by somewhat tight. By somewhat tight, I mean that, so s going to s to the d, that we know can happen by the previous example. We do have examples where we had s monomials when the factors had as much as s to the d monomials. So this log n in the exponent, we don't know if it's needed or not. Maybe that log n in the exponent could go, and maybe the d square could become a d. But there's not hope for improving much beyond that. Okay, so I've mentioned the word arithmetic circuit, and I'll mention it again later in the talk. It's not so relevant right now, but an arithmetic circuit is an object like this which computes a polynomial. You take in variables and field constants and you add and multiply them in some fashion, and you compute a polynomial as the output. And arithmetic circuits are a very well studied object in complexity theory. We might see more of them soon, but understanding, when you're talking about polynomials and complexities of polynomials, arithmetic circuits often show up. And often the kind of question that is studied is, if a polynomial has low complexity, and we define complexity in terms of how many monomials there are, but there could be other measures of complexity. So if a polynomial has low complexity, can you say that its factors also have low complexity? And so this was studied by Kaltofen in the 80s, and he showed that this is true for VP, which is the class of polynomial sized arithmetic circuits. So in a sequence of really beautiful works, he showed that if you have a polynomial which can be efficiently computed by which means by a small arithmetic circuit, then its factors also have small arithmetic circuits. Oliveira showed this result for if a polynomial is computed by a constant depth circuit of small degree, then its factors also have constant depth circuits of small degree. And then there was other works by Datta Saxena Sinhababu and Chu Kumar Solomon studying closure results for VNP, and then there were closure results shown for ABPs and formulas. And the work that I talked about is like a closure result for depth 2 circuits of bounded individual degree, which means so if you have a polynomial which is a depth 2 circuit of bounded individual degree, its factors also have small depth 2 circuits of bounded individual degree. And then using our sparsity bound, whose proof I will talk about, we can use it to show that not only are these factors small, but you can also efficiently devise algorithms for computing what these factors are. So if you have a polynomial f with s monomials in individual degree d, we just show that the factors are also don't have too many monomials, but you can even compute the factors algorithmically in quasi-polynomial time. And if you improve the sparsity bound, you remove the log n. If you improve the sparsity bound from quasi-poly to poly, you would improve the running time of this algorithm from quasi-polynomial to also polynomial. So what I'm going to do now, much of the talk I will devote to the proof of the sparsity bound. How do you prove that factors of sparse polynomials are pretty sparse? And then I'll mention a few words about factoring algorithms. Okay, so let's recap what we want to show. So there's some underlying field. It doesn't matter what the field is, and we have n variables, and f is g times h. And then what we want to show is that if f has only s monomials and every variable has degree d, then the factors of f, so g and h, don't have too many monomials. They're at most s prime sparse, where s prime is not too much larger than s. S prime is going to be s to the order of d square log n, and we're in the setting where d is small. So what we will prove is a slightly more general result. We'll show that if f is g times h, and if g has many monomials, then we'll show that f needs to have many monomials too. So it's the same thing, just I don't know, it's contrapositive. I don't know what it is. It's the same statement said differently. We were saying that if f has many monomials, we want to show that g can't have too many monomials. We'll show that if g has many monomials, then f needs to have quite a few monomials also. Okay, so it's the same statement, just said differently. So basically, for any the way we'll show it is for any polynomial g, which has s monomials, you can't multiply it by some other polynomial h and get a huge cancellation of monomials. There must be enough monomials which still survive. Okay, so that's what we want to show. And the way we will show it, the proof is going to go via convex geometry. So this is what we'll do. So for any polynomial f, you can write it as a sum of monomials. So it's a sum of some coefficient times some xi to the I1, x2 to the I2, and so on and so forth. Take any polynomial f. We can look at the set of exponent vectors of f. By that I mean, so I'll define the set support of f to be, let's look at all the monomials, non-zero monomials which appear in f, and then just look at the various powers of the variables that appear. So if x1 to the I1, x2 to the I2 times xn to the In was made up this monomial, then you look at the n tuple I1, I2, I3 up to In, where these each I1, I2, all these are non-negative integers. Okay, so look at all these n tuples that you get, one corresponding to each monomial. You put them in a set, and that's the support of f. And every element of the set is a point in R to the n, because it's an n tuple of non-negative integers. So you can view it as a point in R to the n. R is the reals. Okay, so your polynomial might have been over any field, even over finite fields, but the support of f is a set which is a subset of R to the n. Now you can define something called the Newton polytope of f, which is just the convex hull of the points in the support of f. So I had a bunch of monomials, I took these exponent vectors, I put them in a set, their convex hull is the Newton polytope. So for example, if f was this polynomial that I've given you, then the support of f would have 4 points in it, 0, 0, 2, 0, 0, 2, and 2, 2. And then the Newton polytope would be the convex hull of these 4 points, which are all in R2. Any questions so far? Okay, so let's see. So now that we've defined the Newton polytope, let me state some properties of the Newton polytope, and then we will use that to prove our sparsity bound. So maybe the most important fact about Newton polytopes that we will use, and this is a result of Ostrovsky from 21, but this is not from 1 year ago, but more than 100 years ago, that if f equals g times h, you take any 3 polynomials f, g, h, where f is g times h, then if you look at the Newton polytope of f, that equals the Minkowski sum of the Newton polytopes of g and h. And the Minkowski sum of 2 polytopes is, you look at for every point in one polytope and every point in the other polytope, you look at the vector sum, and you do this over all pairs of points. It turns out that an object still looks like a polytope, and that's the Minkowski sum. Okay, any questions, then stop me and ask me. But this is not a hard fact to prove, but a basic fact about Newton polytopes. If f is g times h, then the Newton polytope of f is the Minkowski sum of the Newton polytopes of g and h. Here's another fact about polytopes, and I'm calling it a folklore fact. Again, it's not very hard to show, that if for any polytope P, if you let V of P denote the number of vertices or the number of corner points of the polytope P, then, okay, so that's the definition. Then if you start with any polytope A and you take the Minkowski sum of A with any other polytope B, the number of corner points cannot go down, it can only go up. So the number of corner points of A plus B is at least the number of corner points of A and at least the number of corner points of B. So this is just a fact about polytopes, again, not very hard to show. And another easy fact is that for any polynomial f, the number of monomials in f is more than the number of corner points of its Newton polytope. This is easy fact because how did we get the Newton polytope? We took all the monomials corresponding to each monomial, we plotted a point and then we took their convex hull. So when we took the convex hull, the number of corner points that get introduced in this convex hull is at most the original number of points in the support of f, which is at most the number of monomials in f. So the number of monomials in f is at least the number of corner points of its Newton polytope. Okay, so given three facts, let's put them together, and if we put them together, we see that the number of monomials in f is at least the number of corner points in the Newton polytope of f. But the Newton polytope of f is the same as it's a Minkowski sum of the Newton polytopes of G and f. This f should be an H. It's at least this is the Minkowski sum of PG plus PH. So the number of corner points of PG plus PH is at least the number of corner points of PG and at least the number of corner points of PH. Good. So let's remember this. Now notice that what we wanted to show was that if G is any polynomial with S monomials, you can't multiply it by another polynomial H and get this huge cancellation of monomials. You wanted to say that if you multiply G with any other polynomial H, then the polynomial F that you get must still have many monomials. What does this have to do with Newton polytopes? By everything that we showed, it's going to suffice to show, in order to show that you can't cancel out the monomials of G by multiplying it by another polynomial H, it suffices to show that if G is a polynomial, again, of individual degree D and S monomials, then if you can show that the Newton polytope of G has many corner points, then you're done. Because you start with G, the polynomial G, if you show that the Newton polytope has many corner points, then that implies that the Newton polytope of PG plus PH has many corner points, which implies that the Newton polytope of PF has many corner points, which will imply that F has many monomials. So now, in order to prove a lower bound on the monomials of F, we can forget about multiplication of polynomials altogether. We can just focus on one polynomial G, and if its Newton polytope has many corner points, we are done. That will imply our sparsity bound. So I just want to say that a connection between Newton polytopes and sparsity bounds had been made by an earlier work of Dwyer and Oliveira, and it inspired our approach to even look at Newton polytopes in the context of sparsity bounds. So let's recap. So if G is a polynomial of individual degree D with S monomials, we want to show now that the number of corner points of the Newton polytope is large. But notice that in general, for a polytope P, there's no good way of saying that the number of corner points is large in terms of the number of interior points. For instance, you might have this polytope which has 4 corner points and some number of interior points, but you can get polytopes with many more interior points but still just 4 corner points. So how do we prove lower bounds on the number of corner points? So in this, what I drew here, what we did not take into account was, I said, okay, this polynomial has bounded individual degree, and the bound on the individual degree is crucial, and we need to be able to exploit it in order to be able to prove what we want to prove. Okay, so first, an observation that even saying the word, so suppose I want to prove that G is a polynomial of individual degree D with S monomials, then its Newton polytope has many corner points. Even then, we didn't use the fact that G is a monomial. We just treated G as a set of exponent vectors. We just only cared about the exponent vectors in that statement. So in order to prove what we want to prove, it suffices to just forget about polynomials and prove something even more combinatorial, which is that if E is a subset of 0, 1, 2, 3 up to D to the power n, right, and each vertex of the Newton polytope, or each point in the support of G, did look like just a point in 0, 1, 2, 3 up to D whole to the power n. So if E is any subset of 0, 1, 2, 3 up to D to the power n with whose size is S, we want to show now that the convex hull of E. So you look at E as a set of points in R to the n, you look at the convex hull, we want to show it has many vertices, that polytope has many vertices. And I'm just rephrasing it, that if E is any set of points and V of E is the vertices of the convex hull, then we want to show that if E is large, then the number of vertices is many. Or in other words, the number of interior points, the total number of points of E is at most the number of corner points raised to D square log n. And there's no structure, we know nothing about E other than the fact that it's a subset of 0, 1, 2, 3 up to D whole to the power n. Okay, good. So that's what we want to show. That E is a subset of some subset sitting in R to the n. Then the number of interior points is at most the number of corner points to the D square log n. So when we talk about interior points in polytopes, so one theorem or classical theorem that comes to mind is the Caratheodory's theorem, which states, which is, again, it's a very basic, just a linear algebraic fact, that every element of E, since E is an interior point in the polytope, every element in the interior is a convex combination of at most n plus 1 corner points. That's what Caratheodory's theorem says. Any interior point is a convex combination of few corner points. We want to show that the number of interior points is not too many as a function of the number of corner points. So we want to show, for instance, that if we have some number of corner points, V of E corner points, we want to show that the number of interior points is at most the corner points to the D square log n. And all we know that E is not an arbitrary set. E is a lattice point where each coordinate has norm at most D. So here's a wishful thought that we had, and I didn't know if it is true or false, but E is somewhat special set of points. These are lattice points of norm at most D. Maybe you can strengthen Caratheodory's theorem. Maybe every interior point is not just a convex combination of n plus 1 points. Maybe it's a convex combination of much fewer points. Just k points, where k is something like D square log n. Moreover, maybe when you write E as a convex combination of, every point of E is a convex combination of few points, maybe this convex combination is also a uniform convex combination, by which I mean all the coefficients of the convex combination are the same. Suppose this was true, that you could do this. You could write each interior point as a convex combination of very few corner points, and all the coefficients of this convex combination were the same, just 1 over k. If this was true, then we would be done. And the reason is, I mean, then you can have only few interior points. Since each interior point is a uniform convex combination of few corner points, that would imply that there are just few interior points, because every subset of k corner points would determine uniquely one interior point, and then you could prove what we were setting out to prove. So this was a wishful thought. It turns out to be not true, that every interior point of E is a convex combination of very few corner points. But it turns out that though this is not quite true, it is close to being true. It's approximately true in the following sense, that every point of E, it turns out, can be epsilon approximated, and we will do it in the L infinity norm, but it can be epsilon approximated by a uniform convex combination of very few corner points, just O of d square log n corner points. And this is good enough, because this implies, so if each interior point can be approximated by the convex combination of k corner points, notice that since the interior points are well separated, these are lattice points, so the same set of k corner points can't be used to approximate two different interior points. So every k tuple of corner points can approximate only a unique interior point, and so the total number, by the triangle inequality, the total number of interior points is at most the number of corner points to the power k. So this approximate version of Caratheodory's theorem will give us the sparsity bound we are looking for. So let me state this approximate Caratheodory's theorem, and I'll even prove it in a couple of lines. It's not so hard to prove. So we saw it referenced in a paper by Barman from a few years ago, but I believe this theorem is much older than that, and it says the following. So let V be a subset of R to the n, and so this is a set of points, and suppose you know that the L infinity norm of each vector in V is at most D, which is the setting we are in. Then this theorem says that, like, fix any epsilon being a small constant, say 0.1. Then for every interior point of the polytope spanned by V, for every interior point, there's a close by point. For every mu, there's a mu prime, which is epsilon close to mu. So there's a close by interior point, and that close by point is indeed a uniform convex combination of the vectors of just a few vectors which are the corner points of the polytope. And that's exactly what we were looking for, right? We're showing that every interior point can be approximated by a uniform convex combination of few corner points. So that's the approximate Caratheodory's theorem. I'm going to give a quick I'll just demonstrate how simple the proof is once you know what you want to show. So again, so V is a collection of vectors. Pick any interior point mu in the convex span of V. So you can write mu as, by the usual Caratheodory's theorem, you can write mu as a convex combination of some of the vectors of V. So you can write mu as summation ai vi, where the ai's are non-negative and summing to 1, and all these vi's are vectors in capital V. So you wrote mu I as this convex combination. What we can do now is, since these ai's are non-negative and summing to 1, we can view these ai's as defining a probability distribution on the vectors vi. So we think of sampling V1 with probability A1, V2 with probability A2, and Vn plus 1 with probability An plus 1. So let's imagine this probability distribution. We take lots of samples from this distribution, something like 100 d square log n samples from this distribution, and let mu prime be their convex combination, the uniform convex combination. Then it's a simple Chernoff and union bound argument to show from this point that mu and mu prime must be close in L infinity norm. And so you found, so hence given mu, you found a mu prime, which is, there exists a mu prime which is the uniform convex combination of few corner points. And that completes the proof of this approximate Caratheodory's theorem. And then once you have the approximate Caratheodory's theorem, this completes the proof of the sparsity bound as well. It shows that once you know the number of corner points is large compared, can't be too much smaller than the number of interior points, it implies that that polynomial g cannot be multiplied by another polynomial h to cancel out most of the monomials. Okay, so that completes the proof. So I just that completes the proof that I wanted to talk about. I'll just make a few remarks and talk about, say a little bit about the factoring algorithm. So the main question is, like, is our sparsity bound tight? Like, we got some bound, but can this bound be improved? And there was an example given by Saptarishi showing that so we started with an algebraic problem, we translated it into a very geometric setting, and the geometry bounds then gave us the bounds for factors of polynomial. There's an example by Saptarishi showing that the bound we got for understanding lattice points, how many interior points are there as a function of the number of corner points, that bound cannot be improved much. For instance, so he showed that there are n points in 0, 1, 2 to the n. So this is non-trivial. Like, when we did this work, we didn't know that such examples existed. But it turns out you can find n points in 0, 1, 2 to the power n. So that the convex hull contains n to the log n lattice points. So that log n in the exponent is kind of necessary in this convex geometry statement. And this is the same log n which eventually comes back into our sparsity bound when we show that if you have s monomials, the factors have at most s to the d square log n monomials. This is that log n which is sitting there. So the polytope bound cannot be improved much. We don't know if the final sparsity bound for factors can be improved or not, but at least the polytope bound cannot be improved. So if we want to get an improvement to the sparsity bound, we need to use some other information rather than purely this through this polytope route. There's been recent follow-up work giving improved sparsity bounds when the underlying polynomial is a symmetric polynomial. So not for general polynomials, but you impose more constraints to say that if a monomial appears, then all its permutations also appear in the polynomial. So if you know that information, then you can get improved bounds. Okay, so I'll just say I'll wrap up after a few slides on just the connection to polynomial factorization. So the problem of polynomial factorization is given as input a polynomial f. You decide whether f is irreducible, otherwise you output a factorization of f. This is a fundamental problem with applications to list decoding, de-randomization, cryptography, etc. So again, if you're given as input an arithmetic circuit, which is an object computing a polynomial, then Kaltofen and Traeger in the 80s and 90s gave beautiful, highly non-trivial algorithms. They were randomized algorithms for factoring general polynomials computed by polynomial size circuits. And in particular, these works implied that polynomials with small arithmetic circuits have factors which are also small arithmetic circuits. And these are very remarkable algorithms. They are randomized, and there's a very interesting question to de-randomize these algorithms. But it turns out that de-randomization is a little bit tricky in the sense that de-randomizing polynomial factoring is equivalent to de-randomizing something called the problem of polynomial identity testing. Polynomial identity testing is the problem of you're given as input a polynomial computed by a small arithmetic circuit. Decide if the polynomial is identically 0 or not. And it turns out, so it's a very natural problem with lots and lots of applications, but we only know randomized algorithms for this, and we have no non-trivial deterministic algorithm. And this is a fundamental question in algebraic complexity theory. If we can de-randomize polynomial identity testing, this would imply super polynomial circuit lower bounds. So it's believed to be, it's fundamental, but it's also inherently difficult. There was a work from a few years ago showing that de-randomizing polynomial factoring is equivalent to de-randomizing polynomial identity testing for general polynomials computed by arithmetic circuits. But we do know how to de-randomize polynomial identity testing for special classes of circuits. So can you de-randomize factoring for those special classes of circuits? That's a nice question. So for instance, we do know how to de-randomize polynomial identity testing for sparse polynomials. And so that motivated the question of, can you de-randomize factoring for sparse polynomials? And we showed that we in sort of can de-randomize factoring for sparse polynomials, and sort of means there are two big weaknesses in our bounds. One is we can only do it for small individual degree. So for polynomials of small individual degree, we show how to even compute the factors. So what I talked about earlier, we show that the factors are also pretty sparse. We show that we can in quasi polynomial time actually output this factorization and compute the factors of a polynomial with sparsity s and bounded individual degree. And if you improve the sparsity bound, if you get rid of the log n in the sparsity bound, it would get rid of the log n in the factoring algorithm. Again, for d equal to 1 and d equal to 2, this was known prior to our work. For any d which is 3 or more, this gave the first non-trivial algorithm. And I'm just summarizing the two results, and then I will wrap up. So we again show that for any arbitrary field, if f is a polynomial with s monomials in individual degree d, the factors are also pretty sparse. They're bounded by the number of monomials in the factors is at most s to the o of d square log n. And again, so what we know about this bound is that I don't know that this log n in the exponent needs to be there, and I don't know that the d square, maybe the d square can become a d. And then once we have the sparsity bound, we can use it to I didn't talk about the algorithm, but we know how to now get a deterministic algorithm for computing the factorization, and that runs in time quasi polynomial also in S. So the main questions to think about are to make that quasi polynomial into a polynomial. It would be great to get rid of that log n in the exponent, which I don't know needs to be there. And it's also possible that if you're working over fields of characteristic 0, then much better sparsity bounds might be possible, that the d might become a log d. So right now the proof technique I gave was oblivious to the underlying field, but if we can look at the underlying field and get better bounds, I think that's a very interesting question. Getting improved factoring of sparse polynomials is also very interesting, and getting factoring for other classes of circuits where we know how to de-randomize polynomial identity testing. I think that's another very natural and interesting direction to look at. So I will stop there. Thanks everyone, and let me know if there's any questions.
All right. Thank you very much for the nice talk. Are there any questions?
So for symmetric polynomials, is it much improved, the bound? Like
that log n in the exponent is removed. So we know how to. So all the examples I gave right in the very beginning of the talk, they were all for symmetric polynomials. So you couldn't hope to improve the bound better than what those examples gave.
Okay.
So the log n in the exponent has been removed for symmetric polynomials.
Thanks.
Any other questions? That doesn't seem to be the case. So thank you again, Shubhangi, for
Thank
the
you.
talk.
Thank you. It was a pleasure.